Hello, welcome to Unit 5, Lesson 5, Representing Exponential Decay. Your learning objectives for this lesson are to be able to explain the meaning of A and B, an equation that represents exponential decay and is written as y equals A times B to the x power. You will be able to find the growth factor from a graph and write the equation to represent the exponential decay. And you can graph equations that represent quantities that change by a growth factor between 0 and 1. Let's go ahead and take a look at the first activity. So in this activity, we see that there are two different tables and they are partially complete. What you need to do is take a look and see if you can figure out the pattern and complete the table. Go ahead, pause the video and work on that. All right, let's take a look at the first table. So in this table, I can see that as x is increasing by 1, y is increasing by 7.5. 7.5 plus 7.5. So to figure out 4, I would just add an additional 7.5, which is 32.5. Oops. To figure out 25, though, we're going to have to do a little extra math. So since we know that it's increasing by 7.5, we know that that's going to technically be the slope. So we are going to do 25 times 7.5, but then we have to add that initial 2.5, so plus 2.5. And when we do that, we get 190. Looking at the second table, that's a little bit different. Since this one, we can kind of see that this one's increasing more exponentially. So if I look at my first entry, I know anything raised to the 0 power is going to be equal to 1. So this is going to be equal to 2.5 times something to that 0 power, which we don't know yet. All we know is that we're multiplying by 2.5. To figure out the 10, what I'm going to do is first divide by 2.5. So 10 divided by, which is 4. And then, so I know this is going to be 2.5 times 4. Now, I'm not sure what this is as a power or an exponent yet, but I do know that my what I'm being multiplied by 2.5 by is 4. I'm going to repeat that for 40, right? So I'm going to do 40 divided by 2.5, which is 16. So this time I have 2.5 times 16. So now let's pause here and let's think about, well, if I have something to the first power, what does that base need to be in order for it to equal 4? Well, that's pretty simple, right? I know that my base is going to be 4. So my question mark is 4. And that makes sense here, right? This is 4 squared. So I know that each time I'm multiplying 2.5 times 4 to whatever power. So if I think about for when x is 4, I'm going to do 2.5 times 4 to the 4th power, which is 640. And then for 25, I'm going to do 2.5 times 4 to the 25th power. And that lovely number is 976,562.5. So looking at these two tables, we can see that the first one is representing a linear relationship in that we have repeated addition, whereas the second table represents the exponential relationship, or exponential relationship, and that's because we're using repeated multiplication. So that's a big difference between linear and exponential. Linear, you're seeing that repeated addition, which is what caused us to have a straight line, whereas exponential, you're seeing that repeated multiplication, which is what causes us to have more of a curved line. So let's go ahead and take a look at the next activity. All right, in this problem, it says, in order to control an algae bloom in a lake, scientists introduce some treatment products. Once the treatment begins, the area covered by algae A in square yards is given by the equation A equals 240 times 1/3 to t power. Time t is measured in weeks. So go ahead and answer the 3 questions, and once you do that, you can come back to the video. All right, so first question says, in this equation, what does the 240 tell us about the algae, and what does the 1/3 tell us? So in this case, we know the 240 is the amount, of square yards that the algae initially covers. So before any treatment, it's covering 240 square yards. The 1/3 this is our growth factor or decay factor. And this tells us that the area covered a week later is 1/3 the previous week. So the area covered is 1/3 of the area covered the previous week. So this is how much is left. If you were talking about how much it's decreasing by, so we would say it decreases 2/3 each week. So there is 1/3 left. Okay, so for question 2, it says create a graph. When t is 0, 1, 2, 3, 4, think carefully about how you choose the scale for the axes. If you get stuck, consider creating a table value. So what I'm going to do is go ahead and pause my end of the video, finish the graph, and then the next thing you'll see is the graph pop up. All right, so here's a graph. So a few things I want to point out. Notice I did use a table just to kind of organize my work a little bit. When we got to week 2, 3, and 4, I also had to round because it's just easier to graph for the context of the problem. That's fine. For my y-axis, I decided to go up by 20s. For my x-axis, just to kind of spread things out a little bit, I went up by half, but you didn't necessarily have to do that. I also labeled my x and y-axis. So my y-axis is the area, my x-axis is the time. The other couple things I want to point out is that notice that my y-intercept for this problem is 240, and that if I were to connect it, it would look a little bit, or not a little bit, it would look like a curve. And just so you know, just some vocab to go with this, the graphs are, the name of the graphs are asymptotes. Asymptote. Not that you'll be tested on that or anything. All right, question 3 says about how many square yards will the algae cover in 2.5 weeks? Explain your reasoning. For this problem, I didn't necessarily need to know the exact amount. And what we do know, and we can kind of look at the table to figure that out, is that it's going to be less than 27 square yards and more than 9 square yards. A good rough guess would be a number between like 15 and 20 would be a good rough guess. Since we are talking weekly here, you probably could do 1/3 to the 2/5 power, and then multiply that by 240 to figure it out. In situations like this, though, it's going to be a little bit harder to tell for certain because you don't know how the decaying happens in between weeks, right? We don't know if maybe at the beginning of the week most of the decay happens, or is it progressive, especially since we do know, all we know is that it is weekly decay. Now looking at this overall situation, and notice that the graph, as it begins, it decreases more rapidly, and then as the weeks go by, it kind of slows down. And that's kind of a typical exponential decay, right? It starts off quickly, and then eventually it gets slower and slower. So if someone was to say that after 7 weeks all the algae disappeared, would you agree with that statement? And technically no, because you're going to always be multiplying by 1/3. And as I mentioned in the previous lesson, the only way to reach 0 is if you multiply by 0. And since we're never going to be multiplying by 0, technically we will never reach 1/3. Now, realistically, could it potentially get rid of all the algae? Yes. But if we're talking about technicalities and we're talking about specific to the math, we would say no, it never actually reaches 0. All right, let's take a look at the next activity. All right, so this problem talks about having insulin in the body, and insulin is a hormone that is needed to process glucose or sugar in body. For people with diabetes, that's people who cannot process the glucose properly or maybe does not produce enough insulin. Sometimes injections are going to be needed. Once in the bloodstream, insulin breaks down very rapidly, so additional injections are needed over the course of a day to control a person's glucose. So looking at this problem, a patient who is diabetic receives 100 micrograms of insulin. The graph shows the amount of insulin in micrograms remaining in the bloodstream over time in minutes. So taking a look at the graph, we can see that it does have a little bit of a curve to it, so it is that exponential function. So go ahead, pause the video. You do have 6 questions that you need to answer. Once you've answered those, restart the video. All right, question 1. Scientists have found that the amount of insulin in a patient's body changes exponentially. How can you check the graph to support that science claim? So as I mentioned previously, we know that this is decaying exponentially. So that means after each minute, the same fraction of insulin will decay and remain. So to check that, what we can do is to see what fraction of the insulin decays or remains after the first minute, then after the second minute, and so on. If the fractions are the same, then that graph will support the scientist's claim. So check what fraction decays after each minute. If it is the same, it will support the scientist's claim. So how much insulin broke down the first minute, and what fraction of the original insulin is this? So let's take a closer look. So we can see that it starts at 100 micrograms and it goes down to 90. So that means that 10 micrograms broke down, because 100 minus 90 is 10. So we know that 10 micrograms broke down. And then this means that for the fraction, since we know it broke down by 10 micrograms, and the previous amount was 100, that's 10 hundredths, which simplifies to 1/10. For the second minute, this time only 9 micrograms broke down. And down to figure out the fraction, This time we would do 9 over 90, which is still 1/10. So we can see that the fractions are the same. So if 1/10 of the original insulin is breaking down, they want to know what fraction will remain in the bloodstream each minute that it passes. So 1/10 broke down, so that means that 9/10 will remain. And we know that since 1/10 is breaking down, that would leave 9/10 in the bloodstream. So I just want to clarify this a little bit more because we're dealing with two different fractions here. So 1/10 broke down, right? Because we lost 10 micrograms and then we lost 9 micrograms. And each time that is 1/10. The growth factor or the decay factor is what's going to be remaining. So if we're losing 1/10 each time, that means it stays 9/10. So we need that information to finish the table for question 5. So to figure out 4 minutes, I know that I'm going to take 72.9 and I'm going to multiply that by 9/10 because I want to know how much is remaining each time. And when I multiply that, I get 65.61. So I know this is 65.61. Again, to figure out 5, I'm going to do 65.61 times 9/10. And that's about 59.05. Next, it asks you to describe how you would find how many micrograms of insulin remains in his bloodstream after 10 minutes or after m minutes. So to figure out 10 minutes, I'm going to think back to my exponential decay equation that I could create. So our equation is always the amount we start with, so that's 100, times what fraction is remaining. So in this case, that's 9/10, and then that's going to be raised to the 10th power. And if you went ahead and did that math, you didn't have to, but just so you know, that's going to be approximately 34.87, we'll say. So in general, if we don't know any given minute, the expression that we could use is 100 times 9/10 to the m power. We could even take that a step further and we could make an equation. So if I is the amount of insulin remaining in the body, we would say I is equal to 100 times 9/10 to the m power. Just remember the 100, that's what we're starting with. It is also our y-intercept. It's our vertical intercept. Also remember 9/10 is the fraction that remains. You could think of it as we were calculating how much it was breaking down, but you could also calculate how much it remains by just doing 90 over 100, which is 9/10. And then you would repeat that, right? 81 over 90, which is 9/10. And then so on and so on. So you could calculate either way. Just you have to make sure you're choosing the appropriate growth factor or decay factor for the problem, which gets a little tricky when we're talking about decay. It's very easy to mix the two fractions up. Another thing I want to think about is, will there be any insulin remaining in the bloodstream after an hour? And that's kind of difficult to answer because mathematically speaking, we know that it'll never reach 0 because, again, we're always multiplying a positive number by another positive number, meaning we'll always end up with a non-zero positive number. But we do know realistically that medicine does go out of your system eventually. So I just want to remind you that mathematical models are just the simplified descriptions of reality. They're not the end all be all. It doesn't mean that this is true to nature, right? Nature works very differently. So although mathematically speaking, yes, we would say it'll never reach zero. It realistically, we know that eventually the medicine will leave the body completely because, that's why they need the medicine. It's not going to stay in your system forever. So just to summarize a little bit, we talked about exponential decay and what that looks like in terms of graphing. So if we were talking about, for example, this is talking about how much caffeine remains in your body after a certain number of hours. Here we have the starting point. That's our vertical intercept. That tells us that this is how much caffeine was in the body. This is milligrams. 200 milligrams was initially taken in. So whatever drink they were drinking, it was 200 milligrams of caffeine. The growth factor we would calculate by taking how much is in the body after an hour and setting it to a fraction. So in this case, we would do 180 over 200, which is 9/10, popular fraction today. So in this case, our growth factor would be, or you could say decay factor if you want, would be 9/10. And to prove that this was exponential, we could continue to calculate those growth factors between each hour. So for example, I would do, again, 162 over 180, and I see that it is 9/10 again. So we know that that's exponential. When we are writing our equations, it's really important that you're choosing the correct growth factor, because you could have how much is leaving your body versus how much is remaining in your body. So you have to make sure you're reading the problem very carefully. So that's it for this lesson. Don't forget to do your cool down. Thanks for watching.